Our last topic in section 4.1 is solving polynomial inequalities. A polynomial inequality is any inequality that can be written in the form p of x is less than 0, p of x is less than or equal to 0, p of x is greater than 0, or p of x is greater than or equal to 0, where p of x is a polynomial function. So in other words, if you have a polynomial function with any of these symbols, less than or equal to, greater than or equal to, you have a polynomial inequality. Let's begin with an example. Solve the polynomial inequalities given the graph of f of x is equal to x plus 3 times x plus 1 times x minus 2. So our first part to this problem asks us to find the inequalities or find the solutions where your inequality is less than 0. So in this case, we're looking at places on the graph where the function falls below the x-axis. And so if you look, we have a section right here. I'm just going to kind of highlight this section. This is a part of the graph where the graph is below the x-axis. And so what I want to do is I want to write an interval to describe that section of the graph. All right, so that interval is going to start at negative infinity because this, although it's going down very rapidly, it's also sliding over. So eventually it will slide over to negative infinity. And this graph remains negative until we get to an x value of, and let's determine what this x is right here, -1, -2, -3. So from negative infinity to -3, we have a part of the graph where the graph is below the x-axis and where it is negative. Okay, remember that the less than 0 would indicate a negative portion. We also have this part. So starting at -1 and continuing until we get to an x value of 2. So on the x-axis from -1 to 2, the graph lies below the x-axis. And so if we are asked to solve the inequality from looking at the graph, we can say that it's less than 0 from negative infinity to -3, unioned with the interval from -1 to 2. Part B of this problem asks us to find the intervals where the inequality is greater than or equal to 0. So now if it's greater than 0, we're talking about places where the graph lies above the x-axis. So this would be one part. And this is the part beginning at an x value of -3 and ending at an x value of -1. And it says greater than or equal to 0. So because of that equal to, we're going to put brackets. This is also a part of the graph where it lies above the x-axis. So that starts at 2. And it continues on all the way to the right, which would be infinity. So our inequality is greater than or equal to 0 on the closed interval from -3 to -1, union with the closed interval from 2 to positive infinity. So our final example involves solving a polynomial inequality. And what we have here is a list of steps. And so I'm going to read through these steps and then we're going to talk about them with an example. So if we want to solve a polynomial inequality, this is called the sign test method. We want to begin by finding the real zeros of our function. And remember that this means that you're going to set your function equal to 0 and then solve. Okay, so let's just start with that first step. So I'm going to go to my example. we have an inequality, x minus 2 times x plus 5 times x minus 4 is less than or equal to 0. And step 1 says that we're going to find the zeros of that inequality. So we're going to replace the less than or equal to with an equal to for just a second, and we're going to set it equal to 0. So we have 0 is equal to x minus 2 times x plus 5 times x minus 4. And we're going to set each of these factors equal to 0 and solve. So I'm going to do x minus 2 is equal to 0, x plus 5 is equal to 0, and x minus 4 is equal to 0. And so solving these gives me an x value of 2, an x value of negative 5, and an x value of 4. So these are the zeros. Now keep in mind they're also the x-intercepts if they're written as a point with an x and a y coordinate, but the zeros are typically just written with the x values. So that takes care of step 1 in our process. Okay, so step 2 says to place the zeros on a number line, splitting it into intervals. So we're going to take a number line and we're going to mark off 2, negative 5, and 4. So you can see that that's been done here. We've marked off the 2, the negative 5, and the 4, and that completes step 2. And so what it does is it splits the number line into some intervals. So let's talk just a second about what those intervals are. So I'm going to start at the left. The left-hand side of the graph starts with negative infinity, and it goes to negative 5. So that is one interval that we're going to look at. Then we have the interval that picks up on the other side of negative 5 and runs all the way to 2. We have an interval that picks up on the other side of 2 and runs all the way to 4. And we have an interval that picks up on the other side of 4 and runs all the way to positive infinity. So we have 4 intervals if we use these zeros as dividing points on the number line. Okay, so step 3. Within each interval, we're going to select a test point and evaluate our function at that number. If the result is positive, then our function is positive for all x in the interval. If the result is negative, then our function is negative for all x in the interval. Okay, so let's work on this. We're going to take our 4 intervals and we're going to put them in a chart. So let me write them down here. Our first interval is going to run from negative infinity to negative 5. Then we have an interval from negative 5 to 2. We have an interval from 2 to 4. And we have an interval from 4 to infinity. And we're going to select a test point in each of those intervals. So in other words, take the interval from 2 to 4. We're going to pick a number between 2 and 4. Now, it will be easiest if we can pick a whole number. So I think the obvious choice would be 3 in between 2 and 4. Then we want a test point between 4 and infinity. So something bigger than 4, we might say 5. We want something between negative 5 and 2. We might say 0. And we want something between negative infinity and negative 5. So something smaller than negative 5, we might say negative 6. Okay, now you're going to evaluate your polynomial function at those numbers. So remember that our function was, and I'm going to write it down right here, that our p of x is x minus 2 x plus 5, and x minus 4. So what we're going to do is we're going to take our test point and we're going to plug it in for each of those x's. So for the negative 6, I'm going to do negative 6 minus 2, negative 6 plus 5, negative 6 minus 4. So that is going to give me negative 8 in the first one, negative 1 in the second one, and negative 10 in the third one. Which when I multiply those together, negative 8 times negative 1 times negative 10 is going to give me a negative 80. So the result is not so important that I get an 80, but the result is that I do get a negative number. And so what that tells me is that my function, this x minus 2, x plus 5, x minus 4, is going to be negative for any number that you put into that interval, not just the negative 6, but anything in that interval plugged into the function is going to produce a negative answer. So I'm going to write that p of x is less than 0 on the interval from negative infinity to negative 5. And that takes care of my first interval. Now I'm going to do the same thing for the second one. My test point is 0, so I'm going to plug 0 into my polynomial function. So 0 minus 2, 0 plus 5, 0 minus 4. It's going to give me a negative 2 times 5 times negative 4, which gives me a positive 40. So I'm going to write down the word positive on the result, which means that my function is greater than 0 for any x in between negative 5 and 2. Not just 0, but any number I plug in that interval should give me a positive number out. All right, moving on to the third interval. We're going to plug in 3. So we'll have 3 minus 2, 3 plus 5, 3 minus 4. So we have 1 times 8 times negative 1, which gives me negative 8. Again, not so concerned that it's negative 8, but concerned that it's negative, which means that my function is less than 0 on any x between 2 and 4. And our last one, our test value is 5. So we'll plug 5 into our function. 5 minus 2, 5 plus 5, 5 minus 4 gives me 3 times 10 times 1, which gives me 30. And again, that is going to be positive, which means that my function is greater than 0 on any number in the interval from 4 to infinity. And that takes care of step 3. Step 4 says write the solution set consisting of all the intervals that satisfy the given inequality. If the inequality is not strict, meaning it doesn't use the less than or equal to or the greater than or equal to, then the zeros are included in the solution set as well. Okay, so let's take a look at writing our final answer, and that's really all that we have left to do. All right, so write the solution set to the original inequality. Now remember that your original inequality had a less than or equal to 0. So we want to find just those intervals where it's less than or equal to 0. So let's go back to our table. So less than would be this one and this one. So we're going to use these two intervals as our solution. So negative infinity to negative 5 and then 2 to 4. Keep in mind that you do have an equal to underneath, which means that you're going to include the endpoints in your final answer. All right, so the first interval goes from negative infinity to negative 5. So negative infinity to negative 5, including negative 5. And our second interval goes from 2 to 4. And we're going to include 2 and include 4. And we are done with that problem. We now know where our polynomial inequality is less than or equal to 0.